wabarakatuh, and good evening. So this is the video that for our class 27th of October 2021. So this is actually the exercise that I have already showed you in our previous class on Sunday. So but we have still didn't discuss, especially the the question number 3. Okay, so the question number 3, in our class, I said that the solution is wrong, but actually after I go through back, so actually the solution is actually correct. Okay, so pardon me. So let's revise again what is the question is. So we have already been given the voltage source is 120 volt with an angle of 0, and the frequency of these AC circuits is operated under 50 hertz frequencies. Okay, and then the first question is find the average power absorbed by the load, and the second one, um, find the Q before the switch is closed. So meaning that for these two questions, the circuits that will be operated is only the circuit. So what you need to do is to convert the inductance values into its equivalent reactance, which is J50. Okay, and then you need to find the current. Okay, so the current after the calculation is 1.53 with an angle of negative 39.8. Okay, so right now we have already obtained the current with its angle. Okay, and then the voltage across the load is already been given indirectly, where you can see that the voltage across the load is actually equals to the voltage source. Okay, 120 volt with angle of 0. So from that, by using the average power equations, you can obtain the values, which is 70.51, positive 70.5, meaning that this load or this impedance is actually absorbing the power from the source. Next is the reactive power. So simply using the current, we have already obtained the current and the voltage. So you can simply use the reactive power equations. Then you will obtain the value of Q is positive 58.7 var. So positive value here, meaning that your load is actually inductive loads. Okay, inductive load. So if you want to double check whether your calculation is correct or not, so please always look at the load. So if the load is inductive, your calculation should shows a positive Q after the calculation. Okay, that is how you can double check your calculation. Okay, so the last one, which is confusing, okay, but it's actually a very straightforward also. Okay, so find the reactive power supplied by the capacitor after the switch is closed. So when the switch is closed, okay, so the circuit has changed. So we have a capacitor that is parallel with the inductive load, okay, 60 plus J50. So right now, how can you calculate the Q supply or absorbed by this, the Q that actually supplied by this capacitor? Okay, so to obtain that, you need to have the voltage and also the current. So right now, since the capacitor is in parallel with the voltage source, so the voltage across the capacitor is also 120 volt with an angle of 0. So the remaining parameters that we need to calculate is only the current that flow inside the capacitor. So to get the current is actually simply by using the Ohm's law, which is V over Xc. Okay, so the voltage here is actually voltage across the capacitor, which is 120 volt with an angle of 0, while the reactant of the capacitor is calculated as 144.7 with an angle of negative 90. Okay, so you calculate this, do you obtain the current? And simply by using the reactive power equations, you finally will obtain that your Q is negative 49.8 var. Okay. So negative, you have a negative. So when your when your load is contains some capacitors, so your Q will have a negative value. When your load has an inductor, so your Q will have a, a positive Q. Okay. So the overall, so maybe the next question is actually calculate what is the Q total for this circuit. So the Q total is actually the summation of all reactive power inside the circuit. So for the reactive power inside the circuit, you need to see what element inside the circuit. So in this circuit, the element that actually absorb or supply the Q is only inductor and capacitor. So the Q total is you have 58.7 var, and then you have Q. You need to actually QL plus QC, okay? So, and QC is actually negative 49.8 var. So the Q total is the what you call the different actually the deduction of QL and QC. Okay. Okay, right now let's look at example 4. So this is actually the last example. Okay, for our topic. An inductive AC load draws a current 13.4 amperes and a voltage of 208 volt. The phase shift between line voltage and line current is measured with an oscilloscope, and it is 23 degrees. So meaning that this one is theta V minus theta I is 23 degrees. Why theta V minus theta I? Because this give information. This is inductive load. So meaning that the current is actually lagging the voltage. Okay, so that's why you have positive 23 degrees. And since it's shown here is a line voltage and line current, so meaning that it is um, is actually a power system grid. Okay, meaning that this 13 ampere amps is actually IRMS. We assume it is RMS, and this 208 volt is also VRMS. Okay, so the question is calculate the true power. Okay, so the true power is, but if you are using RMS, is a very simple, straightforward, which is VRMS multiply with IRMS cos theta V minus theta I, which is a very simple 208 multiplied with 13.4 cos 23 degrees. So you calculate, so you will obtain the value of your P. While for the Q is also very simple, so V RMS I RMS sine theta V minus theta I, which is 23 degrees. So the unit is var, while for the average power or the true power is the unit is watt. Okay. Okay. So let's continue with example for B. An electrician suggests to you that the lagging power factor may be can be corrected by connecting a capacitor in parallel with this load. So your load is actually inductive load. So the electrician suggests that you connect the capacitor in parallel. So meaning that you have, for example, this is your grid TNB. So this is your original load, which is inductive load. I think I need to redraw back. Okay, inductive R and L. Okay, RL. Okay, this is your load, and it produce P. It will actually absorb P 2.565 kilowatt, and Q is positive 1.089 kilovar. Okay, and electrician suggests to you that uh, actually the power factors can be corrected by connecting a capacitor in parallel with the load. So you just place a capacitor, yeah, parallel. with the load. So because actually the power factor is very much influence your electrical bills. Okay, so in concept, the power factors is actually when you have a voltage, okay, and then you have a current, okay. For example, you have a current. So when you have a different angle, so this is your uh, theta V minus theta I, okay. So the different angle between your voltage and also your current. And right now, as you can see, the current is lagging behind the voltage. So this one, if you have this waveform, so we know that the load is actually inductive load. Okay, inductive load. So when you have okay, actually your electrical bills is a highly also dependent on the different angle between your voltage and current. Okay, so uh, the different angle between voltage and current is actually when you actually cos theta v minus theta I is actually equals to what we call a parameter that we will define later in our class is actually what we call the power factors. So the power factors is will determine um, what you call the electrical bills that will be charged in your bills. Okay, so if you have if you have a different angle between theta v and theta I is very small, maybe in phase, so you will have your power factor is equal to 1 because theta v minus theta I, when this is happen when theta v minus theta I is zero angle. Okay, so your power factors is actually equals to 1. So this is the best one. Okay, we want always our power factor to be like this, but it's actually very difficult to obtain because the power factor is 1 is when your loads it is purely is a pure resistor, which is in real world there is no such load that is a pure resistor because the load because the inductor is very easy to be created. For example, if you have a wire, a cables that actually you want is actually a cables, okay, inside your house, okay, and then it's jump with you have what you call a lot of wires inside a duct, okay, electrical duct, okay, so it will create in inductor is actually an inductor that you are not actually one inductor, but that one is because of the nature. Okay, so that's why is there is no real load that actually can be modeled as a pure resistor. So that's why our home appliance and our electricals load, TV, television, and so on is actually an inductive load. Okay, so inductive load. So depending on the different angle between voltage and current, so it will affect the power factors. And if your angle different between voltage and current is very large, okay, you will have your power factors, okay, is actually less than 1. Okay, in T and B, if your power factors from your home, okay, is less than 0.7, you will be penalized by the TNB. So it is requirement for the resident, the owner, to make sure that the power factor is always larger than 0.7. Okay, I will explain this later, but I want to relate with this example. So actually, when you have a very large Q, it will affect this angle. Okay, so if you have a large inductor, your current will be more lagging. Okay, meaning that the angle here will be very large different. Okay, so how to compensate this inductive load? Because inductive produce positive Q, so to compensate this inductive effect, you can install a capacitor. Okay, you can install the capacitor parallel with the load without modifying the circuit. You just put parallel. Okay, because the total power, total Q or total P is actually independent of how you connect the circuits. It is series or parallel is actually uh, not what you call is not affected. Okay, so you can just install the capacitor here. So for example, if you have your Q 1.089 kilovar, you can compensate this Q. Okay, you can make that your total Q becomes 0. Okay, by making QC equals to negative 1.089 also. Okay, so if your QL is 1.089, so to compensate the QL, so you need to produce QC, which is negative 1.089 kilovar, so that the angle between this one, current and voltage, is 0. Okay. So how to compensate that is actually by installing a capacitor. So right now, the question is actually asks you to calculate the size of the capacitor. So which is very easy. What you need to do is to know what is the equation. Okay, we know that for Q, okay, so for P, we know this is you can use VI, okay, or VI cos theta, or you can also use V square. This one must be magnitude over R, or you can also use I magnitude square R. Okay, the same case goes to Q. So you can use Q VI sine theta V minus theta I. So this one is also theta V minus theta I. Or you can use Q is equals to V square over XC. Or you can use Q is equals to I square XC. Okay, but our circuit is like this. Okay, so the capacitor is connected parallel with the source. Okay, so the source is given already 208. Okay, 208 volt RMS. So you can use this formula. Okay, so your Q is, so we ignore the negative sign, so 0.89 K is equals to this is magnitude 208 square over your XC. So from the calculator, okay, so from the calculator, it gives me the answer of your XC is 39.7 ohm. Okay, so this is J. So this is also negative J. So this is also negative J. Or XC is equal to 39.7 ohm. And so we know that XC is 1 over omega C. So 39.7 ohm. So your capacitor is 1 over Okay, 1 over 39.7 multiply 2 multiply pi multiply with 50 hertz. Okay, so this one will give me the value of 39.7 multiply 2 multiply pi multiply 50 hertz, and then inverse, it will give me around 80.2 microfarad. So you need to install a capacitor with a value of 80.2 microfarad to get your QC equals to negative 1.089 kVAR, because you want to compensate the Q inductor positive 1.089 kilovar, so that your total Q inside the circuit is 0. So when your Q is 0, meaning that you have only P. Okay, so if you have only P, okay, we P is I think 2.5 if not mistaken kilowatt, and your Q inside the circuit right now is 0, right? So what is meaning? Meaning that your voltage and your current, your voltage and current are right now are in phase. Because if you have P but Q, meaning that your load looks like there is no reactance. Your load is only resistive load. So your voltage and current is right now in phase. There is no phase difference between the voltage and current. Okay, so your power factor is high, which is equals to 1. So that is what we want. Okay, so you can actually compensate the Q by installing capacitor in parallel with the load. I think that's all for the class. So we will continue on our next topic for next week, which is I think more on the apparent power and also the complex power. Okay, thank you very much. Assalamualaikum and good night.